Good day, class. Welcome to today's science lesson. Today we are going to explore an invisible yet incredibly powerful topic titled Magnetism, the mechanics, typologies, and applications of magnetism. Pay close attention as we unravel how this amazing force works. Class, let's look at the screen to understand the origin of attraction. Fundamentally, a magnet is a piece of iron capable of attracting other pieces of metal. But beyond the physical material itself, a magnet is defined by the invisible region surrounding it, which we call the magnetic field. Interestingly, permanent magnets have the unique capability to transfer this power, turning ordinary magnetic materials into temporary magnets simply by being close to them. Now, let us study the anatomy of a magnetic field. Look at the diagram. First, we have the field lines, which define the region where magnetic effects dictate how surrounding materials behave. Notice how the force is not spread out equally. The regions of greatest attraction are heavily concentrated at the terminal ends, which we know as the north and south poles. Finally, notice the magnetic threshold, where the magnet acts strictly on specific materials, drawing them into its field of influence. Pupils, let's learn the fundamental rules of how magnets interact with each other. Rule number 1. Unlike poles attract. When you put opposite poles together, like north and south, they create a continuous compounding field that draws the magnets together. Rule number 2. Like poles repel. When you put identical poles together, they create conflicting fields that violently reject one another, forcing the magnets apart. Did you know that the Earth itself acts like a giant magnet? Look at this slide on planetary alignment. A bar magnet that is suspended to swing freely in a horizontal plane is entirely governed by the Earth's own massive magnetic field. Because of this, it will always come to rest with its poles pointing roughly north-south, serving as the foundational mechanism we use for global navigation. Class, let's look at how different objects respond to magnets. On the left, we have magnetic materials, which are actively attracted by a magnetic field, such as iron, steel, nickel, and cobalt. On the right, we have non-magnetic materials, which remain entirely unaffected by magnetic fields. Examples include brass, silver, plastic, rubber, wood, and paper. Next, let's distinguish between the two major typologies of magnets. Temporary magnets are made of soft iron, like pure iron. Their main characteristic is that they easily lose their magnetism, making them ideal for applications where the magnetic state needs to be switched off. Permanent magnets, however, are made of steel. They retain their magnetism for a very long time and are ideal when we need a constant, reliable, standalone force. Now, how do we actually create a magnet? Magnetization is the process of making a material, like a steel bar, able to attract other magnetic materials. There are three main methods shown on the screen. First is the electrical method, where we align the internal structure using an electrical current. Second is the induction method, creating a magnet simply through proximity to an existing permanent magnet. Third is the stroking method, which involves repeated physical alignment across the material's surface. Just as we can create magnetism, we can also destroy it through a process called demagnetization. This is done by subjecting a magnet to highly unfavorable conditions. First, hammering and dropping introduces physical blunt force that shatters the internal alignment. Second, heating very hard introduces high thermal energy that agitates the material and disrupts the magnetic order. Third, passing an alternating current through the magnet completely scrambles its permanent field. Class, pay close attention to this core takeaway regarding the thermodynamic balance of magnetism. Magnetism is not an indestructible trait, it is a very delicate physical state. Maintaining a permanent magnet requires us to actively protect it from unfavorable conditions like physical impact, extreme heat, and electrical disruption, which can easily tip the scale and destroy the internal alignment. Let us look at how magnetism is applied across different industries using a functional taxonomy. 1. It is used in components embedded within electric bells, radios, televisions, and motor vehicles. 2. It is used for separation, actively sorting raw magnetic materials from non-magnetic ones. 3. It is vital for navigation using compasses to help travelers find their direction. And 4. It powers heavy industry to lift massive metallic objects and generate electric currents. In conclusion, class, the entire utility of magnetism relies on manipulating the right material with the right method. By choosing soft iron, engineers can create temporary fields essential for dynamic tools like electric bells. By applying electrical methods to steel, we lock in permanent fields capable of guiding space travelers and producing basic electricity worldwide. It is truly a unified, unseen system. Thank you for listening, and see you in the next class. If you have learned something great today, please click in the subscribe button. Like, share to others. Thank you.